Good day everyone. For today, we will be discussing thermal expansion. This picture shows a damaged sidewalk due to the expansion of the concrete cement during an extremely hot day. This proves that most solids, liquids, and gases expand when they are heated and contract when they are cooled. The illustration shows the particles in solids, liquids, and gases. So, the particles vibrate even when cold. At higher temperature, they vibrate faster and tend to move further apart, taking up more space, making the substance to expand. So the dimensions of a system changes when heat is added or when heat is removed or extracted. So the changes can be in terms of a linear dimension change called as linear expansion, and it also follows that the surface area and volume also changes when there is a change in temperature. And these are called as the volume expansion and area expansion. Let us describe more about linear expansion. So given our object that has an initial length of L sub O, and after a change in temperature, the object will increase its length and will have a final length as L. So the object has a change in length or delta L. So it is convenient to consider the fractional change in length, which is delta L divided by L sub O per degree of temperature change, which is also called as the coefficient of linear expansion or alpha. So alpha or coefficient of linear expansion is equal to the change in length for every initial length divided by change in temperature. From this, we can write an equation for the change in length as the change in length is equal to the initial length or L sub O times alpha, which is the coefficient of linear expansion, times change in temperature or delta T. This table shows the different substances with the average coefficient of linear expansion. So the unit for alpha is per Celsius degree. So if the linear dimension of an object change, it will also follow that the area will change or there is an area expansion. And the area expansion or the change in area or delta A is equal to the initial area or A sub O times the coefficient of area expansion or gamma times the change in temperature or delta T. Wherein our coefficient of linear expansion is related to the coefficient of area expansion, that is twice the alpha is equal to gamma. If there will be a change in the length of an object due to the change in temperature, we can also say that the volume will also change, and that is volume expansion. So the change in volume in an object is equal to the initial volume, which is V sub O, times the coefficient of volume expansion or beta times change in temperature or delta T. And our coefficient of linear expansion is also related to the coefficient of volume expansion, or in 3 times alpha is equal to beta. The table here shows different substances and their corresponding coefficient of volume expansion with unit of per Celsius degree. Let us see some applications of thermal expansion. So thermal expansion is applied in the mechanism of bimetallic strips. So bimetallic strips is composed of two strips of metal that are bonded together. So, given that we have two different metals here at room temperature and they have the same length, and after some time, if we increase the temperature to delta T, the two metals will expand with different amount. So as you can see, when unbonded, the copper expands more than iron because our copper has greater coefficient of linear expansion compared to iron. But when the metals are bonded, the strips can now bend. So these bimetallic strips are actually found in some heating appliances such as flat iron. So bimetallic strips are being used in thermostat to break or connect some electrical circuits. And in flat iron, bimetallic strip bends as the iron heats up. So eventually, the strip will touch another piece of metal. So this completes the electrical circuit that opens a switch so that the iron does not overheat. Also, the position of the bimetallic strip can be altered by a control to set the temperature of the flat iron. We have learned the general rule that as the temperature increases, the object will expand, and if the temperature decreases, the object will contract. However, cold water is an exception to this rule. As we can see from our volume versus temperature graph, the water from 0 degrees Celsius going to 4 degrees Celsius contracts, making its density to increase. And it will only expand above 4 degrees Celsius, making its density to decrease. So water has a negative coefficient of volume expansion or negative beta between 0 to 4 degrees Celsius because instead of expansion, the water contracts even though the temperature increases from 0 to 4 degrees Celsius. So let us try to solve example problems. Example problem number 1. The concrete sections of a certain superhighway are designed to have a length of 25.0 meter. The sections are poured and cured at 25 degrees Celsius. What minimum spacing should the engineer leave between the sections to eliminate buckling if the concrete is to reach a temperature of 37 degrees Celsius? So our substance here is the concrete cement. So the coefficient of linear expansion for concrete cement is 12 times 10 raised to negative 6 per Celsius degree. And our concrete cement will have an initial length of 25 meters. This superhighway was built during an initial temperature of 25 degrees Celsius. And this superhighway will expand if the temperature will increase. So the final temperature is 37 degrees Celsius. So the question is, what minimum spacing must be made? Since there will be an expansion on the concrete cement, there must be spacing between the cement to eliminate buckling. So we are looking for the change in length. Since the temperature increases from 25 to 37 degrees Celsius, we will say that the substance or our concrete cement will expand. And that is the one we are looking for, the change in length or the expansion. And for us to get the expansion or the change in length, that is, the change in length is equal to the original length times the coefficient of linear expansion times the change in temperature. So by substitution, the change in length is equal to 25 meters times 12 times 10 raised to negative 6 per Celsius degree times 37 degrees Celsius minus 25 degrees Celsius. So the change in length is equal to 0.0036 meter, or if it's in scientific notation, that is 3.6 times 10 raised to negative 3 meter. So, the concrete cement will expand at 0.0036 meter. Therefore, the engineer should leave a space that is the same as the expansion of the cement. So, thermal expansion of the concrete cement in our roads are the reason why the roads are made with gaps. So, this is an example of the gaps in the road called as expansion joint. So, this allows our road or bridge to expand or contract without damaging the road. Example problem number 2. At 22 degrees Celsius, an aluminum ring has an inner diameter of 5.00 cm and a brass rod has a diameter of 5.05 cm. So this is our illustration, the aluminum ring, which has a smaller inner diameter compared to our brass rod. If only the ring is heated, what temperature must it reach so that it will just slip over the rod? The second question is, what if both are heated together? What temperature must they both reach so that the ring slips over the rod? So let us analyze the given. So we are given two materials. One is made of aluminum and the other is brass. That's why the coefficient of linear expansion for aluminum and brass are also given. We are also given that both are at initial temperature of 22 degrees Celsius. The initial diameter of the aluminum ring is given as 5 cm. So D sub O is the initial diameter. And for our brass rod, the diameter is 5.05 cm. So again, for this case, our aluminum ring has a smaller diameter, which is 5 cm, and the brass rod has a larger diameter, which is 5.05 cm. And we are asked for the final temperature if only the ring is to be heated. So the aluminum ring must be heated so that its inner diameter will become bigger and the brass rod can now slip over the ring. And the second unknown is, what would be the final temperature if both the aluminum ring and brass rod are heated? If we are about to heat the aluminum ring so that it will expand and will fit in the brass rod, the final diameter of the ring must be 5.05 cm, which is equal to the diameter of the brass rod. And we will look for the final temperature or T sub F of the aluminum ring until it expands to 5.05 cm. Using the equation, delta L is equal to L sub O alpha delta T, and by substitution, delta L is the change in the dimension for the aluminum ring. For this case, this is the change in the diameter, which is 5.05 cm minus 5 cm equals 5 cm, which is the initial dimension of the aluminum ring, times its alpha, times the change in temperature, which is T sub F minus 22 degrees Celsius. Simplifying our equation, we have 0.05 cm equals, multiplying 5 and the alpha will give us 1.2 times 10 raised to negative 4 cm per Celsius degree, and this is still multiplied to T sub F minus 22 degrees Celsius. We can still simplify this by distributing 1.2 times 10 raised to negative 4 cm per Celsius degree to T sub F and to negative 22 degrees Celsius. So it will give us 0.05 cm equals 1.2 times 10 raised to negative 4 cm per Celsius degree times T sub F minus 2.64 times 10 raised to negative 3 cm. Let's combine similar terms and we will have 1.2 times 10 raised to negative 4 centimeter per Celsius degree times T sub F equals 0.05 centimeter plus 2.64 times 10 raised to negative 3 centimeter. And divide both sides by 1.2 times 10 raised to negative 4 centimeter per Celsius degree, and we will have the final answer for T sub F as 438.67 degrees Celsius. So this is the final temperature if the aluminum ring is heated until it reaches the diameter of 5.05 centimeter and will now fit in the brass rod. For the second unknown, we are looking for the final temperature if both the aluminum ring and brass rod are heated. So for this case, the final dimension of the aluminum ring and the brass rod are equal after the change in temperature. So let us derive the formula for the final dimension from the general formula of change in length is equal to the initial length times coefficient of linear expansion times change in temperature. So change in length is also the same as the final length minus the initial length is equal to L sub O times alpha times delta T. Transposing L sub O to the other side of the equation, it will give us final length is equal to L sub O plus L sub O alpha delta T. So we can now equate the final dimensions of our aluminum and brass rod using the given equation. So that is, again, this is the final dimension of the aluminum ring is equal to the final dimension of our brass rod. By substitution, these are the given for the aluminum ring, and that is 5 cm plus the product of 5 cm times 24 times 10 raised to negative 6 per Celsius degree times the change in temperature, which is unknown, is equal to, for our brass rod, that is 5.05 cm plus the product of 5.05 cm times 19 times 10 raised to negative 6 per Celsius degree times the change in temperature. So we can now simplify this. That will become 5 cm plus the product of 5 and the coefficient of linear expansion is 1.2 times 10 raised to negative 4 centimeter per Celsius degree times delta T. The other side of the equation is 5.05 centimeter plus the product of 5.05 and the coefficient of linear expansion is 9.595 times 10 raised to negative 5 centimeter per Celsius degree times delta T. Let us now combine similar terms. So 1.2 times 10 raised to negative 4 centimeter per Celsius degree times delta T minus, we will transpose this to the other side. It will become negative 9.595 times 10 raised to negative 5 centimeter per Celsius degree times delta T equals, on the right side we have 5.05 centimeter minus 5 centimeter. Simplify our equation. We will have 2.405 times 10 raised to negative 5 centimeter per Celsius degree times delta T is equal to, the right side of the equation is 0.05 centimeter. Dividing both sides by 2.0405 times 10 raised to negative 5 centimeter per Celsius degree, and we can now compute for our delta T, or the change in temperature. From this, our delta T, or the change in temperature, is equal to 2079 Celsius degree. Since we are looking for the final temperature of the objects, therefore, the final temperature is equal to the initial temperature, which is both 22 degrees Celsius, plus the change in temperature, which is 2079 Celsius degree. And it will give us an answer of 2101 degrees Celsius. So this is the final temperature for both the aluminum ring and brass rod if they are heated, so that the brass rod can now fit to the aluminum ring. Example problem number 3. Inside the wall of a house, an L-shaped section of hot water pipe consists of a straight horizontal piece 28.0 cm long, an elbow, and a straight vertical piece 134 cm long. A stud and a second-story floorboard hold stationary the ends of the section of copper pipe. Find the magnitude and direction of the displacement of the pipe elbow when the water flow is turned on, raising the temperature of the pipe from 18 degrees Celsius to 46.5 degrees Celsius. Let's analyze the situation. So our object here is the pipe, which has the coefficient of linear expansion as 17 times 10 raised to negative 6 per Celsius degree. The other given are, we are given the dimensions of our pipe, which are 28 cm long along the horizontal, so that is the initial length along the horizontal, or L sub OX, and we are also given 134 cm as the initial length of our pipe along the vertical, or L sub OY. The initial temperature of the pipe is 18 degrees Celsius and the final temperature is 46.5 degrees Celsius. Since the temperature is increased, we expect that there will be an expansion, or there is the change in length. And we are asked for the magnitude of that displacement, or the change in length, and the direction of the displacement, or theta. So starting with our general equation, and that is the change in length is equal to the initial length times the coefficient of linear expansion times the change in temperature. Since we are given two dimensions, and those are the dimension along the x and y, therefore we will compute for the change in length along x and y. So let's start with the change in length along the x, or along horizontal, and that is the initial length along x times alpha delta t. So by substitution, our given are the change in length along x is 28 cm, the alpha is 17 times 10 raised to negative 6 per Celsius degree, and the change in temperature is the final temp, which is 46.5 degrees Celsius minus the initial temperature, which is 18 degrees Celsius. Calculating for this, the change in length along the horizontal is 0.014 cm. Let us compute for the change in length along the vertical. That is, delta L sub y is equal to L sub O sub y alpha delta t. So by substitution, delta L sub y is equal to the initial length along y is 134 cm times the alpha, which is 17 times 10 raised to negative 6 per Celsius degree, and the change in temperature is 46.5 degrees Celsius minus 18 degrees Celsius. Calculating for the change in length along the vertical, that is equal to 0.065 cm. Since we are given the change in length along the horizontal and vertical, we can now compute for the magnitude of the displacement, or the magnitude of the delta L. And that is, delta L is equal to the square root of delta L sub x squared plus delta L sub y squared. By substitution, delta L is equal to the square root of 0.014 cm squared plus 0.065 cm squared. And computing this, we will have the magnitude of our displacement is equal to 0.066 cm. For the direction of the displacement, or the theta, we will compute it using the inverse tangent of the change in length along the vertical divided by the change in length along the horizontal. By substitution, we have the inverse tangent of 0.065 centimeter divided by 0.014 centimeter. And computing for our angle, we have the direction as 78 degrees below the horizontal. So if we would like to figure this out, it is like this is our change in length along the horizontal, this is the change in length along the vertical, and this is our delta L. So 78 degrees is our direction for our delta L. You may now proceed in answering the assigned problem to your class.